Now we got to talk about the direction a little bit more detailed. So that was magnitude. Direction is attractive. The direction is attractive. Really, if we wanted to get into it mathematically, we would write it this way. Actually, if we wanted to say, okay, let's sort of draw these things again. So here's 1, here's 2. You got a force like this of 2 on 1, and you got a force like this of 1 on 2 and 2. And they're really vectors, so we have to have some vector way to write it. So we're going to talk a little bit about the direction. Most of the problems we do in this class won't be so vector-oriented, but I at least want you to understand why this is weird. So if we were going to really write it mathematically, it would be, say, 2 on 1 would be the gravitational constant, g, m1, m2, r squared between them, and then r hat. Oh my God, what does that mean? No, I saw somebody shaking their head, and I see like people upset. Okay, so r hat is the unit vector of the polar coordinate system or the spherical coordinate system. So what it means is if you're doing the force that 2 applies to 1, you're getting this force. You define this one as the origin of a spherical coordinate system, and you say this is the radial direction. Right? And therefore, r hat is a unit vector pointing that way. Right? F of 2 on 1. Right? This is the force that 2 applies to 1, and it's attractive. 1 to 2. Yeah. So you got to have that unit vector on there. Right? But then the deal is like it changes direction when you flip sides. Right? 2 on 1. Where's 2 on 1? 2 on 1. No, I'm sorry. Yes, okay. That's why I'm very mixed up. You put the origin here, and this is still the radial direction. Right? So you want to know the force that 2 applies to 1. So 2 is sitting here, and you want the force that it applies to 1, right? And it sucks on it, right? It pulls it this way. It's attractive. It's in the negative, so there's a negative sign. That's why I'm panicking. Okay, I put the origin in the wrong place. If you put the origin on the source mass and you say, what force does it have on other masses around it? There's a negative sign there to make it pull back. Okay? Yeah. So gravity joke. Like that. Okay? Why am I making this point? So what's weird, though, is this is the one. Now, what if you put it over here? Right? Then you know it would go that way. So basically, the problem is that there's no simple way to describe this Cartesian. Let's try it with Cartesian. Let's just do it in 1D. Okay? So let's try to do this in Cartesian. Let's put mass 1 at the origin of a Cartesian x-axis. All right? You say, okay, I bet you I could write this Cartesian, because we prefer Cartesian coordinates. They make more sense. The unit vectors don't change directions. I hinted something about the malevolence of God earlier. This is it. I'm going to show you why. Okay? So if we put it here, and we put mass 2 here, we could probably write this and say F of 1 on 2, right? Oh, it must be G m1 m2 over r squared, and I guess it must be x squared, because we put it along x, where this is the origin, and this is at x, right? And then we'll just call it I hat, because we're good at I hat at this point. And we say the force of 1 on 2, it's this way. Oh, yeah, so it is negative, right? So you could try to say that. Okay. Left and right. Okay. I'm doing this quick because you don't use this. I just want you to understand where it's coming from. If this, somebody asks what r hat is. If this is the origin of a spherical coordinate system, r hat is just the unit vector in the radial direction, but it changes direction. That's what's weird about r hat. And that's what's horrible about spherical coordinates. If you're at this point, r hat points that way. If you're at this point, r hat points that way. It's the unit vector, just like I hat, j hat, and k hat. But what's difficult about spherical coordinates and polar coordinates is that it's not a constant direction. If you're in a Cartesian system, I hat is always this way, right? It's the plus x axis. I hat, you go over here, I hat, it's always to the right. By definition, that's what a Cartesian system is. In a polar system, as you move around, the r hat direction changes. That's what makes the calculus hard. And there's also a theta direction, theta hat. Oh my God, and it changes direction. And there's a phi hat sticking out of the board. And they all change depending on where you are. That's why we have a class called vector calculus. Okay? If we didn't have to do things in spherical coordinates, there would just be Calc 1 and Calc 2. And everything would be Cartesian, and it will all be easy. But here's the problem, is that the universe is in spherical coordinates. The fundamental interactions of the universe, gravity and electromagnetism, are completely spherical. And I can show you why if we say, okay, no, I'm doing it in Cartesian, everything's fine. You can say, okay, well, what if you put 2 over here? Right? Now mass 2 is over here. So we say, okay, mass 2 is over there, no big deal. Minus g, m1, m2 over, we'll put a negative value in, like negative 3 meters squared, I hat. Which way is that going to make it go? Well, your negative 3 will get squared. It'll be a positive number. You'll have a negative number in front of I hat. It'll say the force is this way, which is wrong, right? The force is this way. So there's no way to write in a Cartesian system this simple equation to describe the force, even for something as simple as just 2 masses pulling on each other. You can't, it's inherently not Cartesian, it's only polar. But our bodies and our minds and everything is easy in Cartesian, but everything's polar. Right? This is my evidence of the malevolence of God. He could have made everything Cartesian, or she could have made everything Cartesian and made everything polar. So I started my own religion over this. It's called agnostic vigilantism, if anybody wants to join it. Okay. So that means, like, I don't know if there's a God, but if I find out there is, I'm going to kick his ass. That's basically what it means. Mostly over this, but also over a few other things. Okay. So if you do lots of really vector-oriented gravitational problems someday, or electrostatic ones, so we won't do it so much now, but in electrostatics we will, this is the problem, right? If you can't just write a symbolic expression for the force at all x, you can't do it, because you have to do it in spherical. If you do it in spherical, then all the calculus just blows up and goes crazy, and it takes a whole semester to learn it. And you don't really learn it in that semester. There's much more.